Right. Okay. So let's start. Good morning once again. So today we are going to start chapter 4, that is the process, in other words, the microarchitecture. So far, we've been talking, we spent a lot of time on chapter 2, which is about the instruction set architecture. We used ARM as our example. We use the same architecture in the lab exercises as well. Now that we are finished with the first set of labs, we'll be moving on to different architecture, MIPS, as I told you. So yeah, so we talked about chapter 1. We started with chapter 1, then spent a lot of time on chapter 2. If you're wondering what happened to chapter 3, that is the self-study exercise that I gave you on arithmetic, integer and floating point arithmetic, chapter 3. Slides I gave you and the book you already have. So read it. It's when I say a self-study assignment, it's not an assignment that you're going to get marked on, but the content can still appear on exams and any other places that you maybe get tested on. So read it. You must read it. It's mandatory to read chapter 3. Right. So in chapter 4, we are going to talk about how we take an instruction set architecture, a given ISA, and implement a microarchitecture based on that. So that is the overall idea. So, right, so let's get into this. Right, so under this chapter, we will look at 2 different implementations of the MIPS ISA. I gave you an overview document of MIPS ISA, which discusses most of the very commonly used instructions, not all, but most of the common instructions there, and a comparison on ARM and MIPS, differences and similarities between ARM and MIPS. So MIPS is again called a reduced instruction set architecture or RISC type processor. Then it has a lot of similarities with ARM, but there are a lot of differences as well. So we will take this MIPS architecture, then we will look at 2 different microarchitecture implementations, or the implementations of this MIPS ISA. One is a very simplified version. We will use that to learn the basic fundamental theories behind this. And then we will look at a more realistic pipeline version. We will talk about more on that later on, probably next week. So this week we'll be discussing the simplified version. Then I will give you an extra assignment of a 3rd implementation, which I will tell you in due course. Right. So first, we need to get a quick introduction into MIPS because we've been using ARM so far. Now we are transitioning into MIPS. So if you remember, in the previous ARM ISA, we defined the instruction categories, 3 different instruction categories. First one was data processing instructions. Second one was data transfer instructions. Third was flow control instructions. So in ARM, data processing instructions were mostly arithmetic and logic instructions where you perform operations on data. Then data transfer instructions dealt with memory, reading and writing to and from memory. Then flow control instructions were about manipulating the instruction sequence, the execution of the instruction sequences, like branches and loops, if conditions, implementing those things. So that is how we categorize the ARM instruction set. In MIPS, we are categorizing these instructions a little bit differently. So we define 3 types of instructions here. First one is I type, second one is R type, third one is J type. So I-type instructions, I stands for immediate. So as you are probably familiar with the concept already, now immediate type instructions will have one immediate operand given in the instruction itself. So instructions like load word or store word, that is this LW and BSW, load word and store word. Then branch instructions like BEQ are also immediate type instructions where the branch target address, the instruction number that you want to jump ahead or branch into, is given as an immediate value. In load word and store word instructions, the address offset that you are referring into the memory can be given as an immediate value. Then arithmetic and logic instructions like add immediate or AND immediate, perform add operation with one immediate operand, perform AND operation with one immediate operand. These things also fall under immediate type instructions. So in I type instructions, there is one immediate operand given in the instruction itself. And there may be flow control type or data processing, data transfer, all kinds of different instructions under that same category, I type. Then in R type instructions, the instruction contains all register addresses, not offsets, all register numbers. So instructions like add, where you take values from two registers and add them together, save the result in a third register. All the operands, sources and destinations are in registers, register numbers. So there are no immediate operands given in R-type instructions. So R-type instructions mostly cover arithmetic and logic instructions like add, subtract, and or, exclusive or, things like that. But there may be certain load instructions falling under R-type category where all the addresses are in registers, base address, offset, everything is given in a register, not as an immediate operand. So there are certain data transfer instructions falling under R-type category as well. Then J-type category refers to jump type instructions, which are used to implement subroutines and function calls, things like that. So you have two different instructions there. One is J jump. It's similar to branch in ARM. You jump to a given offset. Then JAL is like BL in ARM, branch and link. Here it's called jump and link, JAL. So that is used to implement function calls where you need the return address. Right, so that is a very brief overview. Let's try to get into a little bit more about these MIPS instructions. Okay. Right, so when you take R-type instructions, the encoding looks something like this. So as with ARM, we have a fixed length for every instruction, 32 bits. Every instruction is 32 bits wide. Then the first 6 bits from is it 6, 26, 20, from bit 26 onwards, bit 26, 27, 28, 29, 30, 31. Those 6 bits are defined as the opcode or the operation code of the instruction. Then in R-type instruction, obviously you only have register numbers as operands. You have RS, that is RS and RT are source registers, and RD is the destination register. So 3 register numbers. Can someone tell me how many registers you have in the MIPS architecture? You can look it up if you want. How many registers MIPS has? You can unmute yourself and answer.
31.
Yeah,
31.
31. Is it 31 or 32?
32.
If my memory serves me right, we have 32 different registers. Anyone? You can look it up on the internet.
It is 32 bit.
32 bits, yeah. A register is 32 bits wide, but how many registers in the register file?
31.
31, as in 31 are accessible, free to use, but there's a the 31st or 32nd register rather, as we start from 0. 32nd register is the link register. So we have 32 total in the register file. So how many bits do you need to address these registers? Address these registers individually. How many bits do you need?
5.
5 bits, right? 2 to the power 5. So you need 5 bits to address these registers. So in this instruction format, you can see each register number, RS, RT, and RD have each have 5 bits allocated, right? So register number has 5 bits. So the most significant 6 bits are the opcode. Next 5 bits each, the next 15 bits are register numbers. So remaining bits are there to indicate what operation the ALU is supposed to do for this instruction, and then the shift amount. So that is this SHAMT is shift amount from bit 6 to bit 10. Bit 0 to bit 5 is funct, or the function that the ALU is supposed to use. So first 6 bits are opcode, and one unique thing here is for all R-type instructions, the opcode is 0. For every R-type instruction, the opcode is 0. So how do you know what operation to perform for, say, add instruction, sub instruction, XO instruction? How do you know what operation to perform? That is defined under this um, funct field that you see here. So right, so this funct field that you see here, that is the field that defines the function of the ALU that is supposed to ALU is supposed to perform for this operation. And one such function can be shifting the given operand to the left or to the right, arithmetically or logically, if you remember the different types of shifts. So such operation can some operations are given in this funct field are shift operations. So for a shift operation, you need to provide the shift amount as well. How many times are you shifting this particular operand? So that is given by this shift amount field. So that is basically the idea of the R-type instructions. And next, I-type instructions, where we have one immediate operand. As you can see, the least significant 16 bits from bit 0 to bit 15 are immediate operands. So an immediate operand. So instructions like load word, store word, branch if equal or branch if not equal, add immediate and immediate, lot of different I-type instructions are there. I think the majority of the instructions fall under I-type category. So there's an immediate operand and 2 register numbers. From bit 16 to 21 register number, that is the destination register, and bit 25 to 21 is the source register. So it depends on what the instruction that is being executed, but usually RT is used as the destination or the source register for either load or store instruction. RS is treated as the base register where the address is in. The base address is in, and immediate operand will give you the offset. So what will happen in a load instruction, for example, is so a load instruction. Okay, somebody's trying to ask a question. Yeah, you can unmute yourself and ask the question. I don't know the name because the name account says test. Can you unmute yourself and ask the question? Yeah. What is the question? Or is there no question? Okay, if you have a question, you can unmute yourself and ask your question. So, right, so in the case of a load instruction, what will happen is, so a load instruction, what you're trying to do is go to the memory to a certain address, bring the value and put it in a register. Okay, so what will happen is the address of the memory that you're trying to refer to will be defined by this register RS and this immediate value. So register RS will be called, it's called the base register where you have the base address, and immediate value will say from that base address how many spaces that you want to offset in order to reach the address that you want to reach. So once you have the address, you need to go and access the memory with that address and retrieve the data value. And when you have the data value, you can come and put that data value in this destination register RT. And so that is how a load word instruction will operate for an example. Right. So that is, those are the I-type instructions. And next is J-type instructions. Very simple. We only have 2 different instructions, J and JAL, and jump and link. So the opcode for jump and link are, if I remember correctly, numbers 2 and 3. 2 is jump, 3 is jump and link. So R-type instructions, all instructions have 0 opcode. J-type instructions, you have opcode number 2 and 3, jump and link. All the other opcodes that you can form with that opcode bit, opcode field will go under I-type category. So I-type has a lot of instructions, but in R-type, since you have the funct field, the least significant 6 bits, you can define a number of different R-type instructions as well. So some 64 for different instructions, right? So in J-type instructions, we have the opcode and the jump address, the target address, directly given as a 26 bits operand. So that 26-bit operand is the number of instructions that you want to jump ahead or jump backwards. So in reality, the address will have 2 extra bits at the end, which will address individual bytes. But as you know, since an instruction is 32 bits wide or 1 word wide, addresses are always multiples of 4. So the least significant 2 bits are always 0. So because of that, you can ignore the least significant 2 bits and take the next 26 bits. So it's essentially a 28-bit address, even though it is even though we only use 26 bits. Right. Any question so far? Anyone having questions? I will try to take my time and explain everything as we go, because this is where we get into more and more serious things. So fundamental things we need to know very thoroughly. If anyone has a question,
Hello.
you can ask.
Sir.
Yeah.
Hello, sir.
Yeah.
Sir, can you explain about the address part again? Sir?
Address part in which type of
J type.
Okay, right. So J type instruction. Let me just pick up my pointer. J type instruction, you have, so that is your address field, right? So it is 26 bits wide. So let me just bring up the whiteboard. Right. So assume that this is your memory, right? So it has a lot of different memory slots. I'm not going to draw. So then a jump instruction will give us 26 bits as an immediate operand. That is, jump this many instructions ahead, right? So here, if I so this is, let's assume that the current instruction being executed. Okay, so that is the current instruction being executed. So the next instruction being executed, let's assume, is going to be this one, right? The one that comes after it. Right. So that is the next instruction to be executed, and this is the current instruction to be executed. Instruction being executed. So okay, so now if we don't change the PC or the program counter, PC register, which we'll say here, right? So if you don't change the PC register value, the next instruction to be executed is what we have marked as next in this diagram. So if you want to jump ahead instead of that next instruction, if you want to jump ahead into a different instruction, like here, let's call it the jump target. So jump target is the instruction that you want to jump into instead of executing the next instruction in the usual sequence, right? So what you see here as instructions are 32-bit words, right? So each instruction is worth 4 bytes, and the memory address is usually, if you take the full 32-bit memory address, if you take a full 32-bit memory address, that is addressing each individual byte. So the addresses of these instructions are always multiples of 4. I hope you get that. So for example, the address of this current instruction may be address 0, let's say. It's not nice. Right, so address 0, then this next one should be address 4, right? Because the bytes 0, 1, 2, 3 are in the current instruction. That is the current instruction. Bytes 4, 5, 6, and 7 are the next instruction. So the address of this jump instruction should also be a multiple of 4. So 32 or whatever, right? So it must be a multiple of 4 because each instruction in between will consume 4 bytes, right? So when you take that 26-bit address, that is a word address. It's referring to the number of words that the PC should be advanced into, not the number of bytes, right? So when you say number of bytes, if you take the usual address, the typical address, number of bytes, the least significant 2 bits here in that address are always 0, right? Because the instruction, each instruction has an address which is a multiple of 4. Each instruction takes 4 bytes in the memory, right? So once you have address 0, the next one is address 4, next one is address 8, and so on, right? So always the least significant 2 bits in binary are 0. So that is why when we take the 26-bit address, we ignore that 26-bit address that does not contain this these least significant 2 bits. Right? 26-bit address says how many instructions you want to jump, not how many bytes. To get the address saying how many bytes you need to jump ahead to the target, you need to add these least significant 2 bits, or append these least significant 2 bits at the end of this 26-bit address, and it becomes a 28-bit address. So what happens to bits 29, 30, 31? We don't use them. We can't use them because on the immediate let me go back to the slides, because the immediate operand given in the jump instruction is only 26 bits wide, and you can add the 2 bits at the least significant end to make it a 28-bit address, but the remaining bits have to be 0. So you can only jump ahead a number of elements which can be defined by 26 bits, 2 to the power 26 words ahead, or 2 to the power 28 bytes ahead, right? I hope that clarifies the question. Does that answer your question?
Yes, sir. Thank you.
Okay, right. So it's good to clarify these things before we go, because once we start to talk about the actual hardware, we didn't have a very good understanding about all these different types of operands and how they work, what they mean, and everything. Right. So when you get inside the CPU, now we are trying to talk about what happens inside the CPU. When you get into the CPU, the operation, the entire functionality of the CPU can be divided into a few different steps. The first thing the CPU does is fetch an instruction from the memory, right? In order to execute an instruction, you need to get it into the CPU. Instructions are in the memory. Your program is in the memory. Your sequence of instructions are in the memory, like we saw in the previous whiteboard diagram. So you need to fetch those instructions using the PC register or the program counter. So that is the first thing the processor does. Use the program counter. Program counter always points to the next instruction to be fetched into the CPU, next instruction to be executed. So using the program counter register, go to the instruction memory, not instruction memory, not just memory, instruction memory, and fetch that word, instruction word, into the CPU. And when you fetch the word into the CPU, you put it in a register called the instruction register. Usually that is how CPUs are implemented. You put it in a register, but that is not necessary to do in every implementation. The very simple implementation we are going to look at first does not need an instruction register, but it's good to have an instruction register. Right. So once you have the instruction fetched into the CPU, the next step is to decode this instruction, to understand what the CPU is supposed to do with this instruction. And that is primarily defined by the opcode, operation code, right? The 6 bits, the first 6 bits will tell you, the most significant 6 bits will tell the CPU what it is supposed to do with this instruction. For example, if the opcode is 0, the most significant 6 bits are 0, then it is an R-type instruction. Then, based on that, the CPU can identify the format of the remaining bits from bit 0 to bit 26. Yeah. So if it is if you get the opcode 2 or 3, it is a J-type instruction. That means the remaining 26 bits from bit 0 to bit 26 are the immediate value which defines the jump target address. If your code is 0, that means this is an R-type instruction. So the next 5-bit field, next 3 5-bit fields are register numbers. Then after that, you may have a shift amount, and you may have a function field to tell the ALU what you're supposed to do. So otherwise, it is an I-type instruction. So keeping the opcodes width as 6 bits for all these different types of instructions make the CPU implementation very simple. You only have to look at the first 6 bits to decide what the remaining 26 bits are supposed to be, right? So to interpret the remaining 26 bits. So it makes the CPU's implementation much simpler. Then if it is an R-type or I-type instruction, you have register numbers. R-type instruction, you have 3 register numbers in the instruction itself. I-type instructions, you have 2 register numbers in the instruction. Then those register numbers you can use to read the particular register from the register file. In the register file, there are 32 registers as we saw, and you can pick the correct registers out of that to read or write into by the given register numbers in the instructions appropriate fields. So that applies to R-type instructions and I-type instructions. Then if there is an immediate value given in the instruction, like an I-type instruction where there is a branch, or I-type instruction where you have you're loading a word or storing a word. There's an immediate value given. Even I-type arithmetic instructions, we will have immediate values given in the instruction itself. So those immediate values will need to be sent to either the ALU, or in the case of jumps and branch instructions, you need to take the address and update the program counter based on that address. So we will go into more details when we look at the pieces of hardware that is required to implement these instructions. So then in the other thing that you had to do in decoding an instruction is these func and shift amount field, function and shift amount fields, which are available in R-type instructions, only in R-type instructions. So those two fields are supposed to be sent to the ALU function funct field. It will tell the ALU what function, what operation the ALU is supposed to do. Then the SHAMT, or the shift amount field, will tell the ALU if there is a shift operation to be done, this is the amount of shift, the number of shifts to be applied on the operand. So that is the second stage in the CPU. First stage is fetching the instruction. Second stage is starting with the opcode, decode the instruction, decode the different parts given in the instruction. It may be register numbers, maybe immediate values, maybe a function field, maybe a shift amount, right? So different fields given in the instruction, identify them correctly based on the type of instruction. Once you have that done, the next step is to do the appropriate operation, and that depends on the instruction that is being executed. It's the next things to be done are different for different instructions. For example, for arithmetic and logic type instructions or shift instructions, you need the ALU to do that operation. ALU to calculate the corresponding arithmetic operation, addition or subtract, or the logic operation, and or exclusive or the shift operation. If it is a load or store type instruction, you need the ALU to calculate the memory address, because the memory address is usually given as two different parts. One is the base register value, the other is an immediate offset value. So those things you need to add together. So the ALU in load and store operation, the ALU is used to calculate the address of the memory. Whereas in arithmetic or logic type instructions, the ALU is used to do the arithmetic or logic operation on the operands. Then if it is a load or store instruction, once you have the address calculated, you need to access the memory, access the data memory. Note the difference, data memory here, and perform the load or store operation, read or write to go from the memory. Then if it is a load instruction, you will have something read from the memory which needs to be written into a register file. Or if it is an arithmetic or logic or shift type instruction, you need to write the result of the ALU into a register in the register file. So that is the next step, writing the result to a register file. Finally, you need to update the program counter. Usually, if nothing is affecting the program counter, the usual operation is program counter equals program counter plus 4, right? So PC equals PC plus 4. That is, go to the next instruction in the sequence. But in the case of branch instructions or jump instructions, PC value will be changed based on a given immediate value in the instruction itself. So in that case, PC needs to be updated based on the immediate value. Right. So that is the overview of what happens inside the CPU. So a lot of different things happen. First thing is instruction fetch. That is Right. So the first thing we do is this instruction fetch using the program counter. Once you have the instruction fetched into the CPU, you decode the instruction based on the opcode, identify what other fields are there in the instruction. Then once you have decoded all parts of the instruction, you go into the execution and memory access stages depending on what type of instruction you are executing, right? So what happens after that is dependent on the instruction, and you use the different hardware accordingly. You have to use the ALU, you might need to access the data memory, then you might need to write a result into the register file, and at the very end, you go and update the program counter. Right, so let's see how this is done in the hardware. This is a very brief overview. We will go and have a detailed look at all these things as we go on. So, right. Right. Can you see my pointer here? I'm pointing to the program counter on the diagram. Can you guys see it?
Yes, sir.
Red pointer?
Yes, yes.
Okay, that's good. Right. So the program counter here, it is used in the instruction fetch mechanism that we discussed in the previous slide. So instruction fetch mechanism, you go and fetch the instruction from the instruction memory. So based on the program counter, you go to the instruction memory, provide the program counter's address into the instruction memory, and retrieve the appropriate instruction from that address, bring it into the CPU, right? So at this point here, the instruction is inside the CPU. Then at the end, you need to update the program counter at the end of the execution of this instruction. So the usual routine is adding 4 to the instruction, 4 bytes to this instruction's address, current instruction's address. So you are going to the next instruction in the instruction memory by adding 4 bytes, right? So that is the usual case. But if there is, if your current instruction is a jump or a branch instruction, there will be an immediate value given in the instruction, and based on that immediate value, you need to go and update the program counter, right? So note that here we are adding 4. That means this is a byte address, right? What you have in the program counter is a byte address, not a word address. You are referring to a byte, the start byte of the instruction, not the entire word. So here, when you're adding an offset to that, you need to make sure that you add the offset as a byte address, not a word address. Otherwise, you will not be able to get to the correct instruction, or you will not be able to make the correct jump. So you need to add the immediate value as a byte address, not a word address. So keep that in mind. We will see that come into play in future as we discuss this in detail. Right. So that is the instruction fetch mechanism. Any question on that? Okay. So next we have the register file, right? So based on the type of instruction, now once the instruction is fetched into the CPU, we decode it. Some logic circuitry inside the CPU need to decode this instruction, and once you decode it, you have different fields. You have register numbers, you have immediate operands, you have shift amounts and function fields and all that. So if there are any register numbers, those register numbers are used to access the register file here. So register file, you have, as you can see, you have 3 register numbers as inputs. Out of that, 2 register numbers are to read, and the remaining register number is to write to a particular register. So if you recall the R-type instruction format, there are 3 register numbers given in the instruction. So that is where all 3 register numbers are provided into the register file. But in other cases, like in immediate instructions, immediate type instructions, if you have only 2 register numbers given, you only need to provide 2 register numbers into the register file. And when you're reading, you can read 2 values from the register file, and those go into the ALU. Right? 2 different values you're reading from the register file can go into the ALU. Or an immediate value coming from the instruction itself can go into the ALU like that. Right? So a different path. Right. Then the ALU can compute and give you a result. The result may be an arithmetic or logic result, or it may be a calculated address. Right? If the result is an arithmetic or logic result or a shifted result, it can go follow this path and go into the register file to be written into the register, one of the registers given by these register addresses. If the ALU result is a memory address, then you can use that address to access the data memory, to read from that address or to write into that address. If you are writing into that address, you need to provide the data to be written into that address as well, and that is coming from the register file from this path. If you are reading from the memory address, you give the address, you read the data, and that data will come into the register file, and you write that data into the register file. Right? So that covers most of the cases that we have in the set of instructions. R-type instructions, I-type instructions like loads and branches, and everything is covered under what we have in this diagram. Do you have any questions on this? Okay, right. So as you can see, there are places we have some junctions like this, right? 2 different inputs coming from 2 different sides, and 1 output going into some logic element. So you can't just join wires like that, right? You have it's a choice that is being made here, whether you are taking the input coming from this side or the input coming from that side. So there are places like that. So you can't just join wires in such cases. When you have to make a choice, select one from a set of given inputs, pick only one. So in such situations, the logic element that we use are multiplexers or muxes in short. So I hope you're familiar with multiplexers from digital design last semester. Yeah. You implemented multiplexers in your digital design course, yes?
Yes, sir.
Yeah, okay, good. So we'll be using a lot of those when designing processes here. So as you can see, there are in this picture itself, there are 3 different places you need multiplexers. But when we really try to implement this, there will be some others as well, because this diagram doesn't show exactly certain functions of the CPU. Once we include those functions as well, we need some more multiplexers. Right. Now this is the same diagram, replacing those choices here, the red circles that you have here, with multiplexers. So you can see we have a multiplexer in the instruction fetch mechanism to decide whether we are incrementing the address by 4 to go to the next next instruction in the sequence, or to decide whether this is a branch or a jump instruction where we will be jumping to a different target. So pick one from these two different inputs coming into the multiplexer, and the picked or the selected outcome will be given into the program count. So who decides this? It's the control logic. Control logic, or the control unit of the CPU, decides this based on the decoding of the instruction. So it is the control unit is handling the decoding of the instruction, and based on the opcode and the immediate values that you have, it needs to generate all the control signals. You can see a lot of blue lines in this figure. All the control signals that you need to send to these multiplexers, like the one we have in the instruction fetch mechanism, or to the memory to decide whether we are going to write to the memory or read from the memory, or to the ALU to tell the ALU whether you need to perform add operation or subtract operation or shift operation or some other operation. All these control signals are generated by the control unit based on the decoding of the instruction, based on the format of the current instruction that we fetched into the CPU. Okay, so that is a very simple overview of the CPU. We will talk more about this in a few slides ahead. Right. So before we go and talk about these separate parts in detail and how different instructions actually are operated within the CPU using these hardware, we need to go back and revise a little bit about some basic concepts from your previous course, logic design, digital design. So as you have learned in the previous course and even before that, in digital electronics, we encode information in binary. Low voltage is 0, high voltage is 1, logic 0 and logic 1. And when you have signals with multiple bits, you need one wire per bit, right? So when you talk about a 32-bit signal or 32-bit instruction, something like a 32-bit instruction, you need 32 wires for that instruction to travel in parallel. There are mechanisms where you can transmit data serially in sequence using a single wire or 2, 3, 4 wires. But in CPUs where these data are transmitted in parallel, you need one wire per bit. So for example, when you have an immediate value given in the instruction which is 16 bits wide, you need 16 different wires to take that 16-bit immediate value, right? To take and transmit that 16-bit immediate value into a different function unit. So one wire per bit is required. So multi-bit data are encoded on multi-wire buses. Right. So there are different types of elements, logic elements inside the CPU. The one type is combinational, the other type is sequential. So combinational elements can operate on data, and output is always a function of input. So something like a simple AND gate, or even an ALU, and even an adder can be a combinational element where the output is always a function of input. So you can draw a characteristic table and do all the math and define the output in terms of the different input signals that you have in that characteristic table. So I hope you're familiar with this concept from your previous semester. Right. So once that is one type, combinational elements, and the other type are sequential elements or state elements. Sequential elements can store information. It has a state. So output is a function of not just input, it's a function of input as well as the internal state. Right. So combinational elements can be some simple elements like an AND gate where the output Y is equal to A and B, right? Some very simple stuff. And there are complex combinational elements like multiplexes where the output Y here is selected from input I0 or I1 based on this S select S signal. So if S is 1, output is I1. If S is 0, output is I0. Something like that. So that's a multiplexer. That is also a combinational element. Then you have this adders. Adders are also combinational elements where the output Y is the sum of A and B. A and B are multi-bit signals, right? A can be a 32-bit value, B can be a 32-bit value. Then ALUs, where you may not just do add operation, you have other operations as well, subtract, logic operations like AND, OR, exclusive OR, multiply, divide, and all kinds of different things. So the output Y is a function of A and B inputs, and the function needs to be supplied from outside to pick what function should be applied on the inputs A and B. Right, so those are combinational elements. Then in sequential elements, you have say things like registers, right? So these are elements where you have a state, internal state. So sequential elements work with the clock signal. There are different two different types. There are latches and flip-flops, right? Latches are level triggered, whereas flip-flops are edge triggered. So we usually use flip-flops in most of our sequential elements. So in the clock signal here, the sequential element can be triggered on edges like this, transition from logic 0 to logic 1 or logic 1 to logic 0. So in this case, we are taking the rising edge here from 0 to 1, the rising edge, right? At the rising edge, you take the D value, input value, and the current state, and it's given into the next state. So, right. I hope that is there's nothing much to discuss there. You're familiar with these concepts. The only thing to discuss there is the operation in a sequential element happens at the edge here. When we use flip-flops in a register, you take the incoming data and latch them or update the state based on the incoming data at that edge in the clock. Right. So then we will in the CPU we will use things like registers with write control. So only the update happens only when a particular control signal like this write signal here is enabled. So here in this particular timing diagram, write signal is enabled or high here in this starting period. Only if that signal is high, the operation will happen at that edge, at the clock edge. If the write signal is high, you will take the input D into the state queue. Then if you take the next rising edge here in the middle of the diagram, you have the rising edge, but the write signal is low. It is 0. So you don't do the operation. You don't go and update the state queue. Then here you have another rising edge. write signal or the control signal is high, enabled, so you go and perform the appropriate operation. So with control signals, you can add more functionality into a device, and we will be using such control signals in register files and also in memory to uh, decide whether we want to write, when we want to write, whether we are reading, when we want to read, and so on. Right. So because we have a lot of combination, a lot of sequential elements in our digital processors, we will have to use a clock signal. We will essentially have to use a clock signal. Then combinational logic, as you know, happen asynchronously, meaning without synchronized into a clock edge. State elements or sequential elements, they work synchronized into clock edges, right? So in between clock edges, the combination elements can take time to perform their operation, like addition, adder operation. It will take some time. So you say, for example, you read from the register file, that is a state element, you perform some operations, and you write into the register file, also a sequential element. So you can read at that clock cycle and write at that clock cycle, not the clock cycle, clock edge, this rising edge here. But between the rising edges, between the two rising edges, your combinational logic needs to complete the given operation. So there are a lot of different operations that happens in under combinational logic, like say adder, if you have multiplier, and operation or operation. So all those different types of operations should be able to complete within the clock cycle. That means the combinational logic function or the part that will take the longest time to complete its operation. Or in other words, the combinational logic element with the longest delay will decide the clock period, decide the size of your clock period, or define the clock frequency. So your clock cycle needs to be able to accommodate even the longest or the slowest combinational logic element. I hope that is clear. Right. So in our initial implementation or initial design of the MIPS processor, we will implement a single cycle processor. That means an instruction will take a single clock cycle to complete, and all instructions are able to complete within that clock cycle. So that is the idea of a single clock cycle. Every clock cycle you need to be able to complete one instruction. So in that case, we need to define the clock cycle in order to accommodate even the slowest combinational element that we have. So we refer to that as the critical path. So from the instruction fetch into the next instruction fetch, the longest delay path is the critical path, and that critical path will define the size of the clock cycle. Right, so next what we'll be doing is building a data path. A data path is a collection of elements that process data and addresses. So things like your register file, OALU, multiplexes, where all these data travel through are part of the data path. So we will design first a simple data path, a single cycle data path, in steps, step by step. So we will start from that overview design we had a look at earlier, and we will add control logic as required. If you remember, the two main parts inside the CPU are data path and control, and we will refine the CPU step by step, adding data path elements and adding control elements as we develop the CPU. So now that we had a quick recap from our digital logic days, digital design stuff, now we will go into talking about the detailed execution of different instructions inside the CPU. So as we had a look at earlier, the first stage of operation is fetching the instruction fetch. You need some hardware for that, including the program counter. Once you have the instruction fetched into the CPU, the next step is to decode that instruction. And usually this is done through the control unit. Control unit do the decoding and generate the necessary control signals. But in certain designs, you may have a separate decoding unit which may be used by the control to get the decoding done. So it depends on how you want to implement this. So right, so instruction fetch, second step instruction decode. Then depending on what type of instruction you have in your hands, third step is to use the ALU to do some arithmetic logic shift operation or calculate a memory address for memory access. If you have a memory accessing instruction, the fourth step will be to go and access the data memory, read or write from the data memory. Then once you have completed the memory access, or if you didn't have memory access, if your instruction was not a memory access instruction, you need to write your result to the register file if you have a result. Some instruction may not have a result, some instruction have a result. If you have a result, you need to go and write it into the register file. Finally, the last thing you need to do is, the sixth thing is update the program counter. The usual operation in the fetch mechanism is to increment the program counter by 4. That is to go to the next instruction in the memory. Otherwise, if your instruction is a jump or a branch instruction, then you have a target address given as an immediate value. Then you need to use that immediate value to update the program counter. So someone asked a question about this byte addressing versus word addressing. So I'll quickly try to explain it. So here in a whiteboard example, we know that addresses here we used increments of 4, right? Because why did we do that? Because each word we have here is 32 bits wide or 4 bytes wide. So this is a word aligned memory that we have drawn here. So this memory is 1 word wide or 32 bits wide. Right? So that is 32 bits wide memory. So that means if you take a single word here, if you take a single word there like that, that has 4 bytes in it, and each of them has an address. Right? So regardless of, without paying attention to the endianness, let's say this is our address 8, right? Because it's only correct in that sequence. So address 8, when we say address 8, this is how these addresses are going to be defined, right? So here 9, 10 and 11. Right? So the word starting from address 8 is what we have here. This is the word starting from address 8, and that word has bytes from address 8, byte of address 8, byte of address 9, byte of address 10, and byte of address 11. So if you want to go through all these elements, address each byte separately, you need a byte address, right? So that is where this 32-bit address comes in. So let me just say, so this is a 32-bit address, right? That is something, the program counter, it stores a 32-bit address. The program counter stores a 32-bit address. But since the program counter is used to access this instruction memory and it accesses instruction words, not instruction bytes, we don't really care about accessing these 4 different individual bytes in an instruction word. So we don't really care what the 2 least significant bits are, right? So with 32 bits, you can address 2 to the power 32 bytes or 2 to the power 30 words, right? So we don't care about accessing words in instruction memory. We care about accessing words. We don't care about accessing bytes. We don't care about accessing bytes in instruction memory because that doesn't make sense. An instruction word is 32 bits, right? So we want to access words. So if we take only these only the most significant 30 bits, most significant 30 bits, you only take that of our address, ignoring the least significant 2 bits, then we are accessing 2 to the power 30 different words. And we are incrementing, we are going by word, not byte by byte. If you want to go into byte by byte level, you have to use the 2 least significant bits in the entire 32-bit address. So when you have a 32-bit address in the program counter, and when you send that to access to the instruction memory, your least significant 2 bits are typically ignored because we don't care about accessing individual bytes, right? So the address is always a multiple of 4. The individual bytes are the byte two byte addressing bits are always 0, because we are dealing with multiples of 4, 0, 4, 8, and so on. So if you try to write that in binary, you will see that always the least significant 2 bits are 0 because the value is a multiple of 4. Value can be divided by 4 without remainder. So I hope that clarifies the question. So there is a difference of byte addressing and word addressing. Right. Okay, so let's get back to our presentation here. So instruction, this is how the instructions are executed, and let's see what hardware we need to implement different parts. So the instruction fetch mechanism, what are the components needed? Can someone tell me what are the components needed? Hardware components in the instruction fetch mechanism. We know we have the program counter, right? What else do we have? Right. Right. So here we have the diagram for the instruction fetch mechanism. We start with the program counter, and program counter always holds the next instruction's address in the instruction memory, and we go there, go to the instruction memory with the address given by PC. It's a 32-bit register, as this diagram says. So you go to the instruction memory, provide the address into the read address port, get the data from the instruction memory. The data that is in the instruction memory is the instruction itself, right? Instructions in your program. So you get the instruction, fetch it, and put it into the instruction register. Instruction register will hold that instruction for the next clock cycle. And during that clock cycle, you need to decode this instruction, generate the control signals, use the ALU, and do the other operations. So the instruction fetch mechanism will use the program counter, it will use the instruction memory, it will use the instruction register, and it will also need an adder to increment the address of the current address stored in the program counter by 4. By 4 meaning by 4 bytes, right? So essentially you are incrementing not the 0th bit position, not the first bit position, but the 3rd bit position. You are adding 4 to that, right? So that addition may generate carry at each bit position. So you need an adder which can handle carry as well. So right, usual progression of the program in the CPU will need your program counter to increment by 4 every time. That is assuming that you are not dealing with a branch or a jump instruction, jump and link or branch type instruction. If you have a branch type instruction, then this address that will go into the program counter for the next instruction fetch, that needs to be changed. We need to add a multiplexer here and provide the jump target or the branch target address into the program counter. So right, so that is the instruction fetch mechanism. If you have any questions, you can ask now. Okay, so next we will have a look at, so this is very simple, right? Very straightforward. Next, in R-type instructions, what do we need to do? First, there are 3 register numbers given in an R-type instruction, 2 operands and 1 destination. So read the 2 register operands from the register file. That is the first thing you need to do after decoding an R-type instruction. Read the 2 register operands for your R-type operation. Perform the corresponding arithmetic, logical, or shift operation in the ALU. That is the next thing you do in any R-type instruction. Then get the result from the ALU and write that result into the destination register using the destination register number provided in the instruction itself. The instruction provides 3 register operands, 3 register numbers. Numbers 1 and 2 are the first 2 register operands. The 3rd register number given is the destination register where you write the result into. Okay, so here, just to recall what we discussed earlier, first 2 register operands, RS and RT are register operands. RD is the destination register, and function or the funct field is provided in the ALU to tell the ALU what operation needs to be done, whether you need to add the two operands or subtract one from the other and so on. Or if it is a shift operation, the SHAMT field will tell the ALU by how many times you need to do the corresponding shift operation. Right. So these are the hardware elements we need to get this operation in addition to the fetch mechanism, right? So you have three register numbers, RS, RT, and RD. So this is RS and register number 2. Read the register number 2 that you're reading is RT, and the register you're writing into is RD. Then, so these are the register numbers, right? So the 5-bit fields coming from RS, RT, and RD, right? Each are 5 bits wide. They are provided into 3 different ports in the register file. So first address, first register address, second register address, third register address, or the right register address. This is what you write into. You read from the first two and you write into the second one. Note that you need to do the 2 reads at the start of the instructions execution, and you need to do the write at the end of the instructions execution. Okay. Then when you provide the 2 read addresses, RS and RT, the corresponding values can be taken from the 2 read data ports, read data 1 and read data 2. And those data should be forwarded into the ALU as operands, first operand, second operand. So these are 32-bit numbers that we are getting from here, because the register file has 32-bit registers. So you are getting a 32-bit value as the first operand into the ALU and a 32-bit value as a second operand into the ALU. And the ALU operation is, we need to generate a control signal for the ALU operation using the function field. Whether it's an add operation, subtract operation, based on the function given here. Note that this is a 6-bit field, 0 to bit 5, bit 0 to bit 5, 6-bit field, and we are sending a 4-bit ALU operation that is indicating that the ALU can have 2 to the power 4 different functional units, different functionalities. But you can have 2 to the power 6 different R-type instructions. Some of those instructions may be using the same functional unit. The shifting, for example, you can have different types of shifts, but using the same shifting unit. Arithmetic shift, logic shift, you can have implement using the same shifting unit. Okay, and the ALU will generate the result of the arithmetic, logic, or shift operation, and that shift operation, that result from the operation needs to be forwarded and written into this register file. So your ALU result should be forwarded to the write data input of the register file. Then the register write control signal should be sent at the, this is a control signal, remember, register using write control. So write enable signal is it should be sent at the correct time at the end of the instructions execution to write the given data into the register file. Otherwise you may be writing invalid data. Right. So that is the operation of an R-type instruction. Any question? Okay, we will move on to the next type of instruction. Right. So in I-type, arithmetic or logic instructions. Now I-type has different types of instruction, different kinds of instruction, arithmetic and logic. Then load word, store word, memory access type instructions, and branch type instructions. So this is only for arithmetic and in logic I-type instruction. So in those instructions, compared to the previous R-type instruction, you have two register numbers given, one operand and one destination. RS is the operand, RT is the destination, first operand and destination, and the second operand is given as an immediate value. So adding an immediate value or subtracting an immediate value. So that those are the type of operations that fall under this category. Right. So the ALU will do the operation just like before, and it will write the result to the register. So the only difference here is that we are only reading the first register operand, one register operand, using RS here, and RT will define the destination register that we are writing the result into. So you provide the RS address, the 5-bit address, into this read register 1 address port, get the corresponding data from read data 1 port, and provide it into the ALU. That is the first operand to the ALU. The second operand is the immediate value, the 16-bit immediate value. So the immediate value you need to get from the decoder, the control unit will get from the decoder and forward it into the second input of the ALU. Now, note the difference. As the first operand, you are reading from the register file is a 32-bit number. The second operand you are providing into the ALU is an immediate value, which is 16 bits. So you need to do something called sign extension. But you're dealing with signed numbers, so you need to extend the 16-bit input value from the instruction, the 16-bit immediate value from the instruction, into a 32-bit value by replicating the 16-bit or the signed bit of that number. The 16-bit, replicate that for the entire 32-bit, the remaining 16 bits in the 32-bit number, right? So extend the sign bit to make it into a 32-bit number and provide that 32-bit operand into the ALU. And after that, it's very similar. The ALU will generate a result, and according to the ALU operation, whether it's an addition or subtraction or whatever. And once you have the result, you forward that result into the write data port of the register file, and the right address is already given as this RT address coming from the instructions second register number. Right. Any questions on this? Okay, so we will proceed. Right, so next are I-type load and store instructions. Instruction that deal with memory, reading from memory and writing into memory. So, right, that is the format of the I-type instructions. So, first you need to read the register operand, that is the base register. Address of this memory access is given in two parts. One is the base register, right? So in the register that is addressed by this field, in that register there's a 32-bit value. That 32-bit value is a memory address, and that will refer to some memory location in the data memory. And the immediate value given in the instruction is an offset. Whether you want to access exactly the value, exactly the location given by that base register, or you want to add an offset to that. You want to go up or go down with relative to that base address, right? So base address points to some memory location. Whether you want to go to a higher address or lower address is defined by this offset, right? So in load word and store word instructions, the ALU is used to compute the address, that is adding the immediate offset into the base register value, base address value. So that addition is done by the ALU. And again, you need to do a sign extension like in the previous case. So again, you are providing addresses into the register file. RS is the base address, right? So base address is given here, right? RS is given into the first address port of the register file, and the 32-bit value stored there is taken from the register file and provided into the ALU's first input. So that is the base address. Remember that we are calculating a memory location, calculating an address in the data memory. So the base address is taken from the RS register and provide that 32-bit value is given to the ALU. Then in the case of not in the case of, we will have an immediate value to add to that base address. That immediate value is given in the instruction itself. So you take the 16-bit immediate value, perform the sign extension, replicate the 16th bit or the sign bit in the remaining most significant bits, and provide the 32-bit sign extended immediate value into the ALU. So you are adding a 32-bit value to a 32-bit value. Otherwise, you can create errors. You can create problems if you try to add 16-bit value to a 32-bit value if you don't align it properly. So you need to perform the sign extension because these are sign numbers to go up or down with related to the base address. So this is a sign number, and that sign number you need to perform sign extension before providing it in the ALU. And the ALU result is a memory address, the location in the data memory that you want to access. So the ALU operation is always addition because you are adding the base address with the immediate offset. You add those two together. This can be a sign number, positive or negative, and this is just a base address. So the ALU operation in I-type load and store instructions are always addition. Add operation is performed by the ALU, and the result is provided. The provided result is a memory access. Now here we are dealing with two types of instruction. One is load, one is store. In a load instruction, you are reading from memory. You are reading from memory and update register. So for a load instruction, the second register number RT is the destination register. RT is the destination register for load word type instruction. For store word type instruction, RT is not the destination register, but it's the source register where you write, where you read from and write into the memory, right? So note the two different cases. RT, if you're dealing with the load instruction, RT is the destination register, that is you're getting from the memory and writing into this particular register in a load instruction. Otherwise, if it is store instruction, you're reading from this RT register, read it and write it into the memory, right? So two different cases here. So let's have a look at the memory part of this this type of instruction, I type load store. So once the ALU gives you the memory address, that address is given to the memory, right? That is the location that you're accessing. If you're reading from the memory, if it is a load instruction, you read the data from the memory and write that data into the RT register here. And you need to provide the corresponding write control signals to the memory as well as the register file. If it is a store instruction, then you are writing into the memory. So the data that you read from the RT register, the second register that you're reading from the register file, is provided into the write data port of the memory, and the ALU computed address is provided the address port. Then that data from the RT register is written to that particular address location that is given into the memory. Again, you need to provide the corresponding read-write signals to the memory device. I hope this is clear. Are there any questions on this? How the load store instructions are operated? Right. Okay. So next we have immediate type branch instructions. Right. So branch instructions have an immediate value, that is the branch target, then two register values which are the operands. So based on the result of the subtraction of these two register operands, you ask the CPU to change the program counter using this immediate value. So these two are what you're reading from the register file. So you need to read these two RS and RT values, compare them, use the ALU to subtract, and perform the subtract operation. To do that, give us the result, whether they are equal or not, or whether which one is larger or not. So then update the program counter using the immediate value if the branch is to be taken. So we are talking about two basic branch instructions: branch if equal or branch if not equal. So there are other branch if greater than and different types, but what they're really interested in is branch if equal and branch if not equal instruction, those two instructions. Right. Then when computing the target address, you need to do some manipulation as well, because the address in the program counter is a 32-bit byte address with the least significant 2 bits as 0, as we discussed earlier, right? Because we are accessing memory locations as multiples of 4 as words. So when computing the target address, we have a 32-bit value in the program counter and a 16-bit immediate value, which we need to add on top of that current program counter value, right? The immediate value here tells how many instructions you need to jump ahead. The immediate value in the instruction, so the 16-bit immediate value tells, it mentions, it indicates whether you need to jump 5 instructions ahead or 10 instructions ahead or 10 instructions behind compared to the current PC value, the next instruction to be executed. So in that respect, what you're dealing with are words, right? So this is a word address. It's not a byte address. How many instructions to jump ahead in the assembly sequence is dealing with words, right? How many, when you say how many instructions, the unit is one instruction, that is 4 bytes. So this value is a word address. It doesn't have the least significant 2 bits to address individual bytes. So this is indicating or targeting individual words. How many words you need to jump ahead or jump backwards. So you need to take the 16-bit value, append the word displacement or shift that value 2 places to the left. So you will add 2 zeros here, right? Take this value, shift it to the left by 2 to create 2 zeros at the end, at the least significant places. So that becomes a byte address which you can add on top of the program counter. So that is apply the word displacement and then do the sign extension, right? So you take the 16-bit immediate value, shift it to the left by 2 to add 2 zeros here and fill the remaining 14-bit positions, most significant bit positions, with the sign bit to apply the sign extension. So then add that value, add that offset value, address offset, into the existing PC+4 or the next instruction to be executed. That was already calculated by the instruction fetch mechanism. It's automatically calculating the PC+4 value as we saw earlier, right? So in branch type instructions, this is what we need to do. So the hardware looks like this. You are reading two registers. Those are the two operands to be subtracted, one from the other. So operand 1, operand 2, that is RT and RS from the previous slide here, right? RS and RT. So RS and RT are read from the register file and provided into the ALU. ALU operation is always subtract. You are subtracting from RT from RS, and we are checking whether you get 0 or not. That means whether this the comparison, the two values were equal or not, because we are dealing with, we are looking at branch if not equal or branch if equal instructions. So for those instructions, we take this 0 output, whether the result was 0 or not. So this is very similar to the 0 flag in the CPSR, status register in ARM architecture. So very similar. We are not using a status register here, but instead of that, we are using the output, 0 output, the same flag output coming from the ALU. So if the result is 0, that means the two values were equal. If the two values are equal, you either perform the branch or not perform the branch, if it is based on whether we are talking about a branch if equal or branch if not equal instruction. So do the appropriate operation. So that signal, 0 signal, is used by the control logic to control the multiplexer that is added onto the fetch mechanism. So right. So the branch target address, which is this immediate value, right? That is the immediate offset. The target address is calculated using the immediate offset, which is a 16-bit value. Apply the sign extension to get the 32-bit immediate value. Note we still haven't shifted this, so this is still referring to how many instructions you want to jump forward or backwards. So referring to words. This address is referring to words. So this offset. So the offset you shift to the left by 2 in order to refer to bytes, because the PC+4 value in the coming from the instruction fetch mechanism, it is already a 32-bit address, which is a byte address. So you shift the offset to the left by 2, so you are referring to, you also have a byte address. So here you have a byte address with the two least significant bits are 0. Again, here you have a byte address where the two least significant bits are 0. So you are referring to words but using a byte address. So you add these two together, add the offset into the usual next instruction in order to compute the branch target. usual next instruction was PC plus 4. Now you are adding an offset into it to go to a different branch target. Right. So that is the extra functionality you need to implement branch instruction. And now this control unit taking this, looking at the zero input, zero signal, will decide whether to use this branch target address or the original PC plus 4 address coming from the instruction fetch mechanism. One of these two using a multiplexer to update the next PC value. So things to note here are the sign extension done on the immediate value, sign bit replicated, and then shifting the value to the left by 2. So in order to do this shifting, you really don't need a barrel shifter or any shifting hardware. All you need to do is just reroute the wires. That is like, say, now if I try to draw this, now you get a 32-bit signal here, right? So if we just take the least significant signals out of that, that is wire 0, this is wire 1, and this is wire 2, wire 3, and so on, and you have 32 wires like that, right? So that is coming from sign extender. Before giving it into the adder at the top of this figure, you need to add 2 zeros here, right? You need to add a signal with 2 zeros. So let me draw the new 2 least significant wires here. Those are new zeros added, and then wire 2, sorry, wrong color, wire 2 going into the adder to compute the branch target is wire 0 of the incoming sign extended immediate value, right? So you don't really need a shifter. You can just reroute the wires like this. Right? You can just reroute the wires like that in order to perform this operation. So you will note that the most significant 2 wires here will be dropped, but that won't be a problem because those are bits that we added anyway using the sign extender, right? So you will get a signal something like this, right? So these 2 red ones are zeros. These are 2 zeros that we have included there. The 2 red wires are zeros, and the other wires we just rerouted to the next bit position. So it is like you did the shift operation, but you don't really need a shifter because we are always shifting to the left by 2 logically, filling with zeros and discarding the 2 most significant bits coming from this 32-bit signal here, sign extender. So you can just reroute the wires like this. I hope that that is clear. You don't need a shifter hardware. You can hard code it like this. Right. So I only have a little bit more to cover today. Right. Let's go to the next one. Right. So the first cut data path, or what we saw so far, that we are performing an instruction in 1 clock cycle, right? So each data path element can only do 1 function at a time. So if you take the memory, we need to read the instruction, and then we need to read data or write data in one instruction. If it's a load instruction, you need to read the instruction itself and then read or write the data according to that instruction. So you need to perform two operations on the memory. That is why we need to separate instruction and data memories in this particular implementation. So you need the instruction memory and you need the data memory. Both are accessed in the same clock cycle. One for the reading and writing of the current instruction, one for the reading of the next instruction to be executed, right? So all this happens at the start and end of the same clock cycle. So you need the instruction and data memories to be separate. Then when linking all these elements together, composing the full data path, we need to use things like multiplexers, when we need to select from alternate data inputs or alternate data sources, like updating the program counter. There are multiple data sources coming into the program counter. PC+4, the branch target address, and we still haven't gotten to the jump type instructions. So those will add another source into the program fetch mechanism. So multiplexes we will need to use a lot. Right. So considering only arithmetic, logic, and load store type instructions, that is excluding the jump type instructions, this is the current data path, overview of the current data path that we are looking at, right? So we have the register file. Instruction fetch mechanism is not here. Once the instruction is decoded, we have the instruction coming, different bit fields are there. We identify if there are any register fields or immediate fields. The corresponding values are sent into either the register file or the sign extender if there's an immediate value. Now, something I want you all to note. If you're dealing with a load store instruction, let's take, if you're dealing with an R-type instruction, you don't have an immediate value, right? There's no immediate value given in the instruction. But you take the 32-bit instruction and send the different fields here into the register file based on the opcode, right? So since all these circuit executions happen in parallel, not like code that we write in a programming language, when the hardware implementation, all the operations happen in parallel. So some part of the instruction or the least significant 16 bits will be sent to the sign extender, even though it is an R-type instruction, right? So it's an R-type instruction. We send the three register numbers into the register file, but we also send the 16-bit, the least significant 16-bit into the sign extender. So we get the sign extended immediate value here, but that immediate value, it doesn't make any sense because the instruction did not have an immediate value. The number that is coming as an output from the sign extender in that case does not make any sense. So it goes into the multiplexer's input, but we should only take that register file input, register file's output as an input into the multiplexer. So the multiplexer select signal should carefully only take that and send that to the ALU, right? You will get some input here into the multiplexer, but that is not a meaningful input for R-type instructions. So there are a lot of places in the data path that such conditions will happen, such situations will happen. So you need to pay careful attention when you're defining the multiplexer control signals from the control unit. For each type of instruction, for each occurrence, you need to give the correct signal into the multiplexer to select the appropriate input. Otherwise, you will be using meaningless inputs and the desired operation cannot be achieved. Right, so that is the composed data path for arithmetic logic can load store instructions, excluding the instruction fetch mechanism and jump instructions. So this is what we've discussed so far. And here we have added the fetch mechanism as well to that. So this is arithmetic logic load and store instructions, including the fetch mechanism. So the control unit is still not shown here, right? So there are a certain set of control signals that you need to generate based on the decoded instruction and send to this register file, multiplexer select signals, ALU operation, memory reads and write, all those things. So that is the full data path. We still don't have jump instructions here. Right, so I think we should stop here, and from in the next class we will talk about ALU control and the control unit in general, how to generate all these control signals for our single cycle MIPS data path. Okay, so if you have any questions, you can ask now. Do you have any question? Somebody's raising hand. Can you ask a question?
So in this system, we don't have CPSR.
We don't have a status register. CPSR is the status register in ARM architecture. Here we don't.
Okay.
Any other question? Okay, so from next class onwards, we'll talk about the control unit, how to make the control unit in order to control this data path, to generate the necessary control signals based on the instructions decoding. Then, so we'll be getting into more and more complex content as we go on. So if you have any doubts, please get them clarified. I will provide additional resources for you to refer while you're at home, so you can read more and understand. So right, if you don't have any question, we can stop the class. If you have any more questions, I'll give you another chance to ask. Somebody has asked a question in the chat in addressing how can we calculate the immediate value. I hope that was clarified in the discussions that we had just now. How the immediate value is taken and sign extended, shifted, rerouted. Yes, can ask.
Sir, do we have to use more than one clock cycle for one instruction?
In the current microarchitecture that we are looking at, we are trying to fit everything into a single clock cycle. So because of that, we need to delay or expand the clock cycle to accommodate even the largest possible delays that we can have in this data path, right? So we will, after we complete looking at this particular microarchitecture, we will look at different microarchitectures for the same ISA, where different instructions can have different number of clock cycles, can take different number of clock cycles. Any other question? Okay, so I will stop recording now.